why the power generated from the solar cell is DC, and how we can match with the AC grid. We need to design. So next time, not next week, no, maybe 3 weeks or more, we will discuss how to design solar cell and connect it to the grid, to the AC grid. But before that, we need to know how to convert the DC to AC. So we need to know the converter, convert the power or voltage from DC or current from DC to AC. This is called inverter. So next week we will start the design of solar cell, but we will design first the equipment convert the DC to AC. So we will take review for the power electronics devices. We will start with the thyristor, diode, maybe we need it, diode, thyristor, rectifier, and inverter. It's very important because maybe some students didn't take the power electronics class. Okay, so should we cover the power electronics converter with the solar cell design, because we needed a solar cell design. Also, we needed the power electronics equipment, converters, instruments, and design of wind turbine generator also. Okay. So, but today we will study the solar cell, how to generate the voltage across the terminal, output terminal, and solar cell convert the heat and temperature, and light to electric source, to electric power, current power, voltage. Okay. So the solar cell convert temperature or heat and light of the sun to power, to current, voltage, or power. Power is the result of multiplying V times I. Output power is DC, but we need the AC. We will convert the DC power to AC power. Okay. So, first time, how to generate the electricity. See here, first step, light, photon. Applied to electron available in valence band. Valence band. Okay. The electron will excite. Then move from valence band to conduction band. Conduction. So when electron move to conduction band, will leave hole here, hole instead of electron. Electron move to conduction band, here will be hole. Electron negative, holes positive. So negative, positive is diode, right? Diode. Now, so this electron cathode, this anode, hole, okay? This is electricity. Now, so we can represent the solar cell as diode or multi-diodes. Okay? direct. Now, so this is for no. This EV, this EC.
So what is
We
the
have-
what is the value of the band gap?
Okay, sorry, I will change. Sorry.
What is the value of the band gap if the electron move from this band
I
to
will
condition band? Okay.
Okay, see here, we have EV, EC. EV is the energy at valence band. Valence band. And this conduction band. And there are energy band, EG, between EC and EV. Maybe equal to 1.1 approximately 1.1 EV electron volts.
For metals or
Anyway,
EG,
Okay.
yeah.
what for metals?
no, I said the band gap for metals is very small.
For metals?
For others.
Energy joule or electron volt, no matter. Matter is long, okay, but energy
Yeah.
gap is given by electron volt or per joule, but for electronics devices, no, electron volt, okay, 1.1, okay, electron. Now, we have electron. We have electron. So, what does mean EG 1.1? Means the electron need energy more than 1.1 to move from valence band to a conduction band. We need energy more than 1.1 to move this electron from valence band to conduction band. And here, so the energy should be more than EG, okay, more than EG, more than energy band, gap band, energy of the gap band should be more than energy of EG to transfer from valence band to electron. Electron should be the energy of the electron should be more than EG to transfer from valence band to conduction band. Make sense? So now,
The energy of the electron has to be greater than the energy of the
EG.
conduction. The
Oh,
EG.
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 EG. Okay? Of EG. So, now, when the electron transfer from valence band to conduction band, here would be the O. O. Okay? And here, now, electron. Electron already negative sign. It's negative, and this the whole is positive. So now negative is cathode. Okay, so this cathode terminal and positive is anode terminal. Okay, so now we generated anode and cathode terminals of the solar cell. But I don't know if the solar cell consists of multi cells depend on the design. We will design this. Maybe the solar cell consists of 10, 12, and each cell in the one solar cell consists of multi diode, because this is effect of the diode, negative, positive, negative and positive. Anode, cathode, holds electron. This is concept of diode. Okay, so now we don't know how, but we will design and we will calculate. But now, what the equivalent circuit for this one? The equivalent circuit for this one, either we have two circuits, either ideal circuit or practical circuit. We will work on both of them. Okay. See. Do you need this graph? No? Yes? No? Attached with the okay. The rest are okay. So I okay. Now, equivalent circuit model of the ideal practical solar cell. First circuit, ideal circuit, and we will know what the difference between ideal and practical circuit. For ideal circuit, see, this means the incident light, okay, from the sun or in the any radius source. Upstairs lab we have light, okay, and you light to panel, okay, and this panel will generate DC. This is an emulator, but actually it's set up the solar cell outside of the building, okay, to take temperature, actual temperature, and actual light, okay, from the surrounding, from the sun or from anywhere. So now we'll generate current. This current. Okay, current, and this current, we say is equivalent for diode, for anode, cathode. This current will follow this diode, okay, and give I and positive, negative V across the diode, and this is I diode. And this I photon. See now, the direction is very important. This I photon, this I diode, this direction, from positive to negative, not from negative to positive. The diode should be from positive to negative. And this current goes to the load or to the grid, to the converter, any equipment we can connect here. Next time we will connect, in our design maybe we will connect DC chopper. So we need to study DC chopper again. Maybe some students took the power electronics class, but sure I will start on the basic. I will start explain all fundamental power electronic converter, okay, and then design. Next week we will start to design. Now, here maybe we will connect load direct, the load DC, or maybe connect the DC chopper, or maybe connect to the DC grid, or maybe connected to inverter. If we want to supply electric AC or AC sources. Depend. So this part design or required for the design. If you have DC load, okay. DC load, maybe you will connect the DC load direct to this, or maybe you need more voltage, so should be connect step up or push converter, DC to DC converter, or maybe you need high current, low voltage, step down, connect step down, or maybe the load. AC, TV or any load, okay? So we need to connect DC to AC, DC to AC converter, DC to AC converter, no converter, okay? This is depending on the question. I will give you a question. Design solar cell circuit with the load. I will give you the specification of the load. Maybe DC, maybe AC, okay, and we will design with given indicator. Now, this circuit consists of current source, diode, and we have voltage, current. So now, I photon or I pH, it will, according to Kirchhoff current law, first law, Kirchhoff current law supposes the entering current at the point equal to the leaving current. So I pH equal ID plus I. So now, I pH equal I diode plus I. Where this first equation, where I pH, the photo generated cat in ampere, in milliampere, okay? Why? Okay, maybe this current is very small, 0.1 or 100 milliampere. Okay, we can increase the value of the current by using multiple cells, okay, to generate more current, also more voltage. Okay, now we will design this one. Okay, design. Now this one cell, just one cell, okay, one section, one cell. When I see one cell, I will show you one cell. I photon.
Right.
Yes.
For each cell, is it, what should the value of the current, is it the type of the cell
I will
used?
mention now. Just I want to show you the one cell, okay, to,
So there's different kind of cells?
yes.
Okay, thank you.
Sure. This model, this consists of maybe million, 2 millions of cells, okay, of cells. Million maybe diode, okay, million diode, okay. So each cell generate I photon, okay, or I photon. To then the source take it from this point and this point. This is total from the cells, all cells, and the voltage, current and voltage, because you know the voltage now. See, let me again show you this. The voltage, if we take the voltage across the diode, we know the voltage across the diode 0.3 if we use germanium, or 0.7 if we use silicon. So first of all, to generate 0.7 only, no, we need 12 volt or 24 volt or any volt, any DC volt. So now this circuit actually is designed as multi-circuit connect together. Depend on the design of the circuit. Okay, this decide this number of the size of the load, will decide the number of the solar cell used. Okay, the load. So in our design, we will start from the load to reach to the sunlight or temperature. Okay, the sunlight is random. Also the temperature random. We cannot get steady state temperature, maybe rise or at this moment is the temperature is 50 Fahrenheit as example. After 2 minutes will be 70. After half hour will be 40. Random. Okay. This random will I will show you how to convert the random function to the steady state voltage at the output. Okay, using MATLAB program. Okay, as a simulation. Now, so multi-circuit for this one, we'll concentrate one solar cell, okay, and the photo-generated current is IPS, and I diode, again, IT is I diode, ID, the diode, current, I is the current goes to the load, or okay. Now I diode. Sorry, I diode. by KBT minus 1. It's I diode. Or I diode equal IS exponential V over VT minus 1 and here delta.
Those subscripts by K, right?
KB, K sub V times T,
Okay, so
and it's a
we-
Q, yes.
Just like a regular P in this cow.
Okay, it's egg, okay? I will explain what this mean by egg. I think it's N of 1. Yes, right. Now, what is mean by Q, KB, T, eta, and VT? First, what is mean by IS? IS is the saturation current. Saturation current is very small current, okay, generated at reverse bias operation. What is mean by reverse bias? I will explain now. Okay, IS and V is the applied voltage in volt for both equations. Okay. And eta is emission coefficient. Silicon equal eta equal 1. Germanium eta equal 2. Okay. Just write this one. We want to this one. Take it. Right? Okay. Already I will upload the lecture note to Canvas to be first, okay? But take your time to write. Now, so eta is emission coefficient depend on the type of the material used for the diode. Maybe silicon eta equal 1. And if we use germanium eta equal 2. Okay? Now, VT, what is mean by VT? This is the volt equivalent to temperature. Volt equal 26 millivolt or 25 millivolt. Some references take it VT as 25 millivolt, and some references no, say 26. Why? Because it's 25.65, so approximately 26 volt. This is VT. So now VT. Do you need this? Okay. Yes? Okay. Take it.
Well,
No.
I got it down. I need to do the BT.
Okay. Now VT. It's thermal voltage VT equal KT divided by Q. K or KB, same. K or KB. KB and approximately point 026 VT, approximately 26 millivolts, 1.026 volts. Now Q is the electron charge. And Q equal 1.6 times 10 power minus 19 coulomb. The unit of the charge, coulomb, millicoulomb, microcoulomb, coulomb, generally, okay? Check the units. Now, KB is also a constant. What is mine? Constant. Where KB equal 1.38 times 10 power minus 23 joule per Kelvin. See, we have three types of temperature units, either Kelvin, Celsius, or centigrade, or Fahrenheit. Okay, then here per Kelvin, joule per Kelvin. Okay, it's fine. You can convert it to other units, no problem. But at the end, VT will be 26 millivolts. Okay, and T is the absolute temperature and Kelvin. Okay, and get this. Sorry. You have a question? Yes. Electron charge, Q, and coulomb. Yeah, the unit of the charge, coulomb. Okay? Yeah. T, what do you mean by absolute temperature in Kelvin? Means the room temperature equal 27 standard. Okay, 27 degree
Celsius.
centigrade. Yes, Celsius. Okay, 27 plus converted to Kelvin plus 273. Okay,
Yeah, for
so temperature in Kelvin equal
270.
temperature in Celsius plus
270.
standard 273 is the constant, and why we suppose it T temperature of the room 27 plus 273 equals 300. Okay, so TC equal TC equal 27 degree centigrade. Okay, so room temperature. So TK equal 27 plus 273 equal 300. Get 300. Okay, any question please? Now, now, if we calculate VT, KV equal 1.38 times 10 power minus 23 times temperature 300 divided by Q 1.6 times 10 power minus 19. So 1.38 times 10 power minus 23 times 300 divided by 1.6 times 10 power minus 19. Equal 0.0258. Okay, so VT, I will write this one, VT equal KV, T divided by Q, KV equal 1.38 times 10 power minus 23 times temperature 300 given Q 1.6 times 10 power minus 23 column, so equal 0.025875 volt or approximately 26 milli. Any question please? It's basic from electronics.
Q 1.60 times 10 to the negative 19, why 23?
Oh, sorry, yes, 1.619, yes. It's basic from electronic or semiconductor.
Yeah, we'll just
So, okay. So now, VT, this is voltage not across the terminal, no. Across the terminal is here. V 0.7 or 0.3 or 0 if ideal diode, okay? But this VT, this volt equivalent for the temperature or thermal voltage generated by each cell. By this VT, the thermal voltage generated by each cell. So now we have two types of temperature. Temperature of itself, of the diode, okay, and temperature from the surrounding area or body, okay? Temperature from the sun, or weather, and here is VT. VT, this V will convert it to temperature, then temperature, okay, we'll convert it to voltage, okay? So we can generate voltage from this thermal, from the effect of the thermal, and this is VT, this voltage, I call it so now, voltage, two terminal voltage, V terminal, V thermal and V terminal. V terminal, this one, this V terminal, this V, okay, and this V thermal, okay, two types of the voltage, the diode equation. Now, the diode equation, any question about this one? Now, according to this equation, okay, the relation between I, D, and V is exponential. And in reverse bias, this is forward. This is meant by forward. Forward bias is forward bias region. And reverse bias is this is minus IS, and this is VC, VC now. Okay, this reverse bias. Reverse bias. Okay. Why this exponential and why this minus IS? We will discuss this point. This is for the characteristic. Any question about the characteristic? Now, why the forward bias is like exponential here, and why the reverse bias is constant, and why at this voltage the current will go negative and higher, and I will explain. Okay. First region, forward bias. Forward bias means this PN, diode, okay, and this is injection, J. Okay. We suppose the diode in forward bias, so the positive of the DC volts connected to P and negative connected to N. So the current will be followed as I diode. Positive, this is positive, negative, this positive, negative, positive to positive, negative to negative. Okay? Because P means P holds positive and negative electron. negative, positive. Positive to positive, negative to negative is forward bias. Forward bias. See, I told you IS is very small. So the current ID equal IS E V eta VT minus 1 or equal IS E V eta VT minus IS. Just distribute the IS or expand the bracket here. So IS exponential minus IS. So forward bias region IS exponential V divided by eta VT more than minus IS. So ID approximately equal to IS exponential V eta VT. So
Could you move down?
the current will be like exponential curve. Okay? The relation between I, D, and V exponential. Why? Because we can neglect IS in milliampere, microampere, okay? So, but IS exponential V over eta VT more than IS, so we can ignore IS and ID equal approximately IS exponential over eta VT, where eta 1 or 2 will depend, take it 1. Because most cells fabricated from silicon, using silicon, okay?
Why
We'll discuss the type of materials.
Why they don't use from Germany?
Because silicon available
Everywhere.
more, everywhere, more than.
But the band gap
Germany.
for Germany is direct band gap. For silicon is
Yes,
indirect band
we
gap.
will discuss this concept
Okay.
next time, what the difference between maybe silicon or perovskite. I will explain
Okay.
more than silicon or germanium material used. Okay? We will discuss later, sure. See, this class most concept about solar cell and wind power. Why? Because thermal or bio or different other type of renewable energies, no mathematical model, no. The USA is solar cell and wind turbine and hydro, more than other renewable energy sources. So we'll focus on this one. Maybe next summer there is a special topic, solar cell and wind turbine class. I would suggest to post it next summer. Okay? Same this one, but we will discuss just the out design, not deep for electron and holes or okay, just solar and wind turbine. Maybe next summer we will suggest this course. Okay, so now in the reverse bias region, IS EV eta VT less than minus IS. So now using this equation or this equation, we can ignore this term, so ID equal approximately minus IS. So minus IS, this minus IS, minus IS. reverse bias. The current equal minus IS constant. Why? Because IS is constant, not exponential. Not exponential, not sine, not cosine, just minus IS. Minus IS is number. Maybe 5 milliampere. 10 microamperes. Not saying this exponential, multiplied by exponential V over. This is no exponential function, but here it's constant function. Okay, so minus minus. Now we reach to VC. So check VC. What is mean by V zero? Okay, and the reverse bias, when we apply more voltage, here, for forward, it makes it first for forward, this one. P and positive, negative, and this one, small junction. This junction. Is V. But for reverse bias, no. This P and this junction. Wide junction. Reverse bias. It's V. Okay. It's forward and this reverse. See the difference? Why? For forward, P and positive. This positive and this positive. So this positive will pull the positive ion to other side, and this negative put the other electron to the other side, while Pn reverse bias, no, this will put the holes on this, the electron on this side and the holes this side, okay? Holes, electron, so while here electron, holes, different, so large depletion region. At Zener voltage, when we increase the Zener, the voltage applied in reverse bias, positive, negative, P and V. If we increase V equal VZ, so all the diode will move to depletion region. All this is depletion region. Okay, so this is depletion region. Okay, this depletion region. All the diode will be depletion region. So a high current, because we reach to breakdown. So this one now is break down. Break down. Break down. At Zener diode. Okay? Break down. This down. Any question? Yes? Any question? Breakdown, yeah. I, okay, that's I, it as denoted this as PV, out from PV, okay, this I, PV, and this diode again, this one, and this is I photo, okay, and this I diode, and this positive negative T, okay. Any question, please? No? No audience? No? Everything is okay? Again, IPH, ID, IPV, PV, for the solar cell or output goes to the load part of it. Goes to the load, okay? Solar cell output carry. Okay. Now, this current again we can write as IPV equal IPH minus ID. Okay, ID is exponential. ID is exponential. This one, so this one here. IPH minus IS exponential V over eta VT minus 1 is IPV. questions, right? Or
Yeah, we did.
fine? Answer? Just we substitute IT sub from the driver equation to get IPV or same IPV, okay, output current from the cell, from one unit. One unit. It means here, okay?
Yes, but Pablo, can we present VT somewhere in the circuit or start?
VT,
Can we present
VT inside the
inside
diode.
the diode?
Yeah, inside the
Oh, okay.
diode. This is the thermal
That diode.
voltage. Yeah, of the diode. Okay? It's not 0.7
It's not-
or 0.3, no. 0.7 or 0.3.
It's very small.
Across the diode.
Okay, but this VT inside. Yes.
Is VT exists in any diode or only because we're dealing with the solar?
At 300 temperature, okay, at 300 temperature, and because the other term constant, and we suppose that the temperature, room temperature 300 is equal 26. For silicon, for germanium, same. Because see where is the BT? See, depend on K, E, Q, T. K be and constant.
Right.
T may be temperature of room temperature or different temperature will change. So if we rise the temperature from 27 centigrade to 100 centigrade, okay, VT will change, increase. Okay? So it depends on the room temperature. Okay? But standard we taking room temperature 27. That's 27 centigrade. So plus 373 equal 300. And get it. Okay? Any question, please? Yeah, take your time to write. Okay? This is all mathematical model for the ideal circuit. Now, the practical circuit. Right? The practical circuit, there are two resistors. R shunt and R series. And this IPH is V plus minus. Now this I diode and this I shunt and this IPH, this current IPH. Here, IPH, sorry. IPH equal I diode plus I shunt plus IPV. And again, I diode equal IS exponential V over eta VT minus 1. Sub this equation and this equation. And I shunt, R shunt, this voltage equal RS IS. Here, you can say IS. Okay? IS. Same IPV, but this IS. I shunt equal IS RS. This derivative is not required. Okay? Just the last equation required. Okay, but this. Okay. RS plus V terminal. I will explain what is meant by V terminal. Or V terminal. V, same thing. Okay? Or IS RS equal IS RS plus V. Now, IPH or IPV equal IPH minus I saturation exponential V over VT eta VT minus 1 minus V ideal plus IS RS divided by R shunt, where I ideal, I will explain what is meant by I ideal, V ideal, sorry. V ideal is the voltage at ideal. Ideal is voltage. This voltage called ideal. This voltage here, V ideal. Where V ideal equal V plus IS RS. This one. This is the mathematical model. If you thesis or master project with me, he draw the circuit diagrams for ideal case and practical and write the mathematical model. Okay? If you need it, I will give you already spread. I have Microsoft Word, okay, and also the circuit diagram using Visio. I have it, so I will provide. Okay, but should be includes in your report, dissertation, thesis, or master project. Okay, should be included. If your project includes part of renewable energy, sure. Solar cell or wind turbine should be included this one. Okay? And now when we work on the project, we're working hybrid resource. Hybrid resource includes solar cell, wind turbine, or increase to one source, hydro source. Okay, any question please? So the ideal, why we say this ideal voltage, V ideal, this V ideal, because same the voltage across the diode in ideal case, right? So we say this voltage is ideal, V ideal, positive, negative, V ideal, okay? Positive, negative. This V ideal. Any question, please? Any question? Right now? Okay, 15 minutes. Okay, take a break now. Okay, 15 minutes. Okay, because I want to start with performance analysis, characteristic of the solar cell. Yes, this one. Last.
Yes, yes.
Down?
Yes.
Right. Start with the other. We analyze the ideal and practical circuit. Now, then we'll start with the performance